kind of MDI operation. And the last one is related to I/O bound application, where you are reading and writing to disk so much. So these are the 4 types of MDI workloads that you can find in different scientific applications. So let's talk first about our motivation here. So GPU computing. So GPU are leading now the compute power everywhere. All the supercomputers everywhere, you are relying on GPUs, especially with AI and large language model now. You need GPU to process larger models. And these GPUs has some kind of MDI operation. And the last one is related to I/O bound application, where you are reading and writing to disk so much. So these are the 4 types of MDI workloads that you can find in different scientific applications. So let's talk first about our motivation here. So GPU computing. So GPU are leading now the compute power everywhere. All the supercomputers everywhere, you are relying on GPUs, especially with AI and large language model now. You need GPU to process larger models. And these GPUs has some kind of features or characteristics that we need to focus on. One of them is related to the computing itself. For example, the recent H100 GPU from NVIDIA has reached to very high performance for processing floating point operation, 64-bit double, single and half precision, and they reach, for example, with double precision to 30 teraflops per second, and with single precision to 60 teraflops per second. This is ignoring the tensor core technology, where you can actually double this these numbers, or maybe more than this. Also, it has a very large memory bandwidth, 3.35 terabyte per second. It also has this NVLink to speed up the communication between the GPU and CPU, reach to 900 GB per second. Comparing to the CPU, of course, we cannot compare anymore. So if you can do something on GPU, you are gaining a very high acceleration of your application, and also very fast communication between the GPUs and between the GPU and the CPU. So for example, this is the recent Intel CPU, Zephyr Rapids, with just 2 teraflops per second and memory bandwidth 300 gigabyte per second. So the key insight here that GPU are providing massive higher flops and memory bandwidth. However, we need the application to maximize this arithmetic intensity. So we need more focus on doing computation more than communication, or even more than sending and receiving things between the processor and the memory. So why compute bound wins? Because when we are talking about the GPU, it can utilize the GPU very well. It can scale excellently on the GPUs. It also provides high flops per watt. When we are talking about, I heard one question on the first presentation talking about the energy efficiency. So also here, GPUs are very important because it's less energy consumption compared to the CPU, and per flops. And it can easily be optimized. If you can time your algorithm using task-based parallelism, or doing any kind of parallelization that can optimize or tune the huge number of cores on each GPU. At the same time, if your application is a little bit communication bound, you have a problem here, because you are not gaining a lot of your GPU. You are sending and receiving over the network. GPU needs to wait. Also, this reduces the scalability, and also wasting energy by having those processing unit not doing anything and just waiting for sending and receiving data. So bottom line, what we need here is GPUs. The current GPUs shine when you have a compute bound application. And of course, this is something that motivates all the scientific fields or domain scientists to move their algorithm from computation, from communication based to computation based, more than doing send and receive here and there. So let's talk about the application I'm focusing on in my presentation is climate weather forecasting. So climate weather forecasting, there is currently 3 ways to do modeling and forecasting for climate weather. One of them is actually the main or the most important way is using BTE models or using physics to do climate weather modeling and forecasting. And you can find earth scientists. People are dealing with those kind of models like WRF, FV3, ICON, and other models. All these models depend on understanding the physics of the Earth. Then based on this, it starts to do the forecasting. This is now something that's used everywhere in industry and also with the government using those kind of models. However, when you scale these models, you have a problem. All of them actually depends or they are communication bound. So they are splitting the data between the processing units, doing small things, then again, communicate, doing sending some small data from here and there, then doing computation again. This is very hot for the MPI operation. I send, I receive, weight, reduce, as you can see for different models. There's some operations that are used frequently with those models. But again, if we return back to accelerating those models on GPUs or moving the current models to GPUs, we have a problem because most of the time the GPUs will be idle and cannot be used. So this is one way. The second way is to use AI, and this is actually now a lot of people are trying to use the AI, and especially this vision transformer dealing with the data of the Earth as images and build some kind of connections and correlation between the images. This is something good, especially with the existing of very scalable framework like DeepSpeed or other frameworks that can run on supercomputer very easily and very efficiently. But actually, those models are still not mature enough to rely on them. So this is what I was talking about, physics-based model and data-driven model like AI, or to go with the third dimension, which is spatial statistics, which I am representing today on my presentation. Spatial statistics is another way to understand, and this is also very mature method to model the climate weather data and use it for forecasting. But for decades, spatial statistics method had a problem because it depends on linear algebra and actually dense linear algebra. And with the complexity of doing those operations on supercomputers, usually you have a limit that you can not go beyond. And compared to the complexity, the memory and computational complexity for the physics-based methods, it's actually replaced spatial statistics for decades. But now with the existing of GPU and also with having some smart way to adopt the spatial statistics method, now it's come again to the surface to, okay, let's use it. Let's try to see if we can gain advantage of the current supercomputers and also current GPUs and replace physics-based method with spatial statistics. So I will give an introduction about what I mean by using spatial statistics for climate weather modeling. Usually, spatial statistics are using Gaussian distribution or Gaussian process to be able to model the data. The problem related to climate weather modeling is a very easy problem. You have a set of locations distributed in a certain region. Let's here talk about the globe. So we have a set of locations in the whole world, and I have, for example, on the simplest format, that each location has one observation, like a temperature. So I know a temperature on each location. I have, for example, longitude, latitude of the whole Earth. So in each point intersect between each longitude and latitude, I took one observation, which represented by a vector y. Okay, then you can easily model the data that you have historically if you add the time as your dimension and use what we call maximum likelihood estimation function. This maximum likelihood estimation function is try to build a correlation between the data on space and time that you have about a specific variable or a set of variables, then using an optimization algorithm to optimize this likelihood function to minimize it and try to find the set of parameters, statistical parameter that can use to explain the model or explain the data that we have, which we call statistical modeling. Okay, if you look to this equation, it's actually very close to the machine learning thing. You are doing kind of optimization to optimize a set of parameters, but instead of having this neural network with a lot of neurons and also the connection and the weights, you just have a covariance matrix. So you need linear algebra here. Okay, so this covariance matrix you need to build with a certain way, then start to optimize this function. One of the very popular way to build this covariance matrix, a function called Mattern covariance function. Okay, this Mattern covariance function again build this covariance matrix where each cell in this covariance matrix represent a correlation between two different locations. When you have very close locations, this correlation should be strong. When you have very far correlation, this correlation should be weak. For example, if we are reading the temperature, it's most probably that the temperature in New Jersey is very close to the temperature in New York. But having the temperature in Jeddah, for example, is not that related to New Jersey temperature. So this correlation function or covariance matrix are doing this kind of understanding of the correlation between different locations based on the distance. This MLE, actually, we worked on this here at our group for more than 8 years now, and we got the Gordon Bell Prize last year about one of the contribution we did on this covariance matrix. We played with this covariance matrix using linear algebra, inserting low rank approximation, having mixed precision, trying to take advantage of high performance GPUs on running something like half precision, while trying to keep the accuracy of the application for the modeling and forecasting as acceptable as possible. So instead of adopting very low precision on our covariance matrix, we had this adaptive way to represent some numbers on the matrix using low precision and some very important numbers with a higher precision. Okay. Then recently we start to say, okay, this is very good, but even with this method, even with trying to get advantage of correlation, the GPUs and different precision, the maximum number of locations that we can model is about, for our GPU, is about 30 million spatial location. This is very good if we are considering here one time slot. But if you are talking about 3 dimension, 1 dimension is the space, the number of spatial location, and the time, the number of time slots, and also the number of variables that you have. You need to multiply these 3 numbers. So this 30 million covariance matrix, which we actually able to run on the whole frontier supercomputers last year, is still not enough to beat the physics-based method and or even the vision transformer methods. So we moved a little bit to the approximation using statistics again. So this algorithm we call VK approximation algorithm, and it's a way to approximate the Gaussian process that I just described in a very easy way to not dive into statistical and mathematical equation here. As I said on the covariance matrix that we have, we need to build the correlation between 2 different locations, any 2 different locations I have on my data set. However, this is not that important because, again, you can ignore very far locations from your location because it's very weak correlation. And this should not impact your accuracy on the modeling and forecasting. So this is how VK approximation built. So instead of building a correlation between one city and all other cities, it's enough to just take the neighborhoods. This neighborhoods to a certain point, which we call here nearest neighbor. So I can decide New York, the far city that I need to take it into account when I model the New York temperature. For example, I will say something like Columbus. This is the first. But if I'm talking about, for example, San Francisco, no, I will ignore it when I model GFK. But at the same time, if I'm modeling something close to San Francisco, I should take take it into account. This is a simple way to explain what's going on with these all equations that we have with VK approximation. Why this is important? Because now we can reduce the complexity from n cube in computation and n square in memory. We can reduce it to reach actually to m multiplied by n locations. So where m is the distance, or sorry, m is the number of nearest neighbor that you are taking into account when you model each point. So the motivation here is this: we need to reach to a billion level. So 30 million is not enough, as I said, when we talk about 3-dimension. We need to reach to the billion level. So our next step to model, or using spatial statistics to model the whole globe as the BDE is doing in a very efficient way and also in a very accurate way. Okay, so this is one thing. Second thing is not just to use Gaussian process for climate weather modeling, where your dimensions is just 2 or 3 dimension. XY when you are talking about temperature, or if you are talking about temperature and the sea, you have XYZ 3D. Some other application also can use Gaussian process to do modeling and use it in different application. For example, aerospace components and automotive design, environment modeling, what we are mentioning here, or even drug discovery. All of these applications can use Gaussian process, but they have a problem related to the dimension. Using the location as XY or XYZ is not enough. Some of these applications have more than 15 dimensions that we need to take into account. So we care about large problems and also high dimension, 2 different things. So this is block VK algorithm pipeline. I will explain it and then we will go to the computation explanation. So what we are doing is very easy. First, you need to start with clustering. You need to cluster the data that you have to see actually who is close to me, which location is close to my location. And you need to do clustering because you need to build this nearest neighbor algorithm for each location, not just in general, okay? So we start with clustering. Then on each cluster, we can do nearest neighbor for each point on this cluster. This makes your life easy than doing a nearest neighbor algorithm for all the data that you have. Once you have this and you know for each point which location you can use, in this case, you can build your covariance matrix. I will also not go in details on this. And you do batch linear algebra operation. And we are using Magma for this. So once you build this, you have your own location, just patch your operation. And actually, once you reach to step 3, you are patching on the GPU that you have. And there is no communication at all between different GPUs. Because if each location has his own data to model himself or his data, he can only patch it on single GPU without communicating with the others. This is the main point. Where is the communication that we have here? We have the communication on the selecting our nearest neighbor, as I will discuss now. So let's go step by step with the algorithm. So if we assume that we have 4 workers here, GPUs, CPUs, we have workers, then we have a bunch of data coming to us and we need to start modeling this data. The first thing is to do partitioning of the data. So I will give each of those workers a set of data from what I have here, okay? The data that I have here should be ordered to be sure that all the data that I have here is very close to each other, okay? So for example, if I'm talking about the globe, I will give the US data to one GPU, I will give Europe data to another GPU. So I'm also taking the distance into account. But remember that these kind of partitioning depend on 1 dimension or 2 dimensions. But if I have more dimensions than this, this is why I need to have a k-nearest neighbor algorithm that can help me to get the closest point to each point I have. Then the second point, I will start with clustering. Each worker will do a clustering internally just to cluster the data it has. So I will know that this data will consider close to each other. The other data will consider to each other, and I will do the clustering. Again, if you think that, okay, it's easy, I can just clustering because I'm looking to XY dimension. But when you talk about another application with 15 dimension, your partitioning will not give you your nearest neighbor because you need to build your cluster and do nearest neighbor on all the dimension that you have. Once you have your nearest neighbor for each block, you can start doing the GPU computation or GPU computing, batch computing. Now, I will do this for each GPU, or each CPU, depends on the worker that you have. So, okay, this is totally independent. Yes, but your problem will start now. When you consider the nearest neighbor, for example, to this point, you have a problem because some of the point on another GPU can be relevant to you, and you need to take this into account. So yes, you can start with the nearest neighbor that you have on your worker or on the same processing unit, but also you need to be sure that you don't have other relevant points on other processing unit. And this is where the communication or MPI is coming to our application. So what we start to do is we start to build a radius, a circle, and this circle depends on the distance for all the dimensions that you have. Then once you define the circle, then in this case, you can define the points that are close to you, okay? And you start doing this internally on all your points. This is very easy. But I need also to ask other processing unit to send the data that they have to me based on this R. So what I'm doing is choosing a center point for each block and use it to compare it with the center point of the block that I am looking for. If those 2 points has a distance less than R, so this means that I will need the whole block to come to me so that I can select some points out of it. So each block has a center, and I need to compare each center of each block with the others, okay? So in this case, I will ask this node, for example, to send me this block. Maybe that block also, maybe also this block. It's based on block-based selection of the blocks that we have here. So we are doing this in 2 steps. First is to choose a candidate, which we called cursor candidates, coming from outside using this lambda. And this is, we are sending the data using MPI all to all. So we are sending data, maybe 1 block, sending it to many blocks, to many nodes, based on the selection or based on this lambda. So there's a lot of communication happening here, and this is a bottleneck for our algorithm. Once we have what we want on our nodes, so it's easy. Just go with searching for the neighbors in the internal points and external points that you just received, and go independently without any kind of communication. And this is the only point, and this is remind me again with the AI, where they have this MPI all reduced. We have the same thing. If we can solve this bottleneck using MPI, then we can accelerate our algorithm very well, because everything else will happen independently. So I have some accuracy graphs here. I will go very fast because I know maybe this is not very oriented to performance that we are looking for, but I will just explain here one application and show some results out of this application. This one of the application outside of the climate weather modeling related to satellite drag data set. So when you have the satellites in the space, there is some variable that impact this satellites and drag it to north, east, west, and usually they are simulating this offline, then they can understand what will happen in the space. So we have here 8-dimension input with different spaces, O, O2, oxygen, nitrogen, and others, and all of this impact the velocity, the temperature. So we need to model this and understand what's going on. I will just show here some results, maybe to give the insights about the importance of Gaussian process. First, we need to know which parameter of which space or which type of these O2, O, nitrogen, and other impacting more the satellite drags. So we are simulating this using Gaussian process. We are getting and forecasting which variables is more important. And we found, for example, the 6th variable, which is here, represented by N1, 2, 3, 4, 5, 6. The hydrogen is actually more impacting the data that we have. As you can see, the relevance is very high. And you can see different levels of different dimensions. Also, you can see here the mean square error of predicting the drag, this drag of a satellite, if we can predict it very well or not. And this is also some prediction results you can find on our paper that I will put at the end, a lot of information about the scientific application here. But what we care about more is the performance, okay? Regardless of the data set that we have, how far we can go from the dimension perspective and also from the data perspective. So we did some experiments on A100 GPU and Grace Hopper superchip on the GSC center, and actually they gave us a good number of nodes to try on and we obtained a good scalability there. So let me jump directly to the performance here. So first we start with the weak and strong scalability on the A100 GPUs. We were able to run on 512 GPUs 1 billion points, 1 billion spatial points. Let me remind you about our Gordon-Bell limit was 30 million by 30 million covariance matrix, which is 30 million spatial location. Using VK approximation and also using modern GPU, using the approximation, we're able to scale this from 30 million to 1 billion on just 512 GPUs. The 30 million spatial location, we model it on the whole frontier supercomputer. And you can see here the weak scalability and the strong scalability results with different number of spatial location. This is on 2 million point, and this is from 2 million to 1 billion. As you can see here, we have some problems related to the strong scalability when we increase the number of GPUs. And actually, this is coming from the step of the MPI all-to-all, because this is actually a bottleneck now. We can do very fast batch operation independently, but once we reach to this communication at the CPU level, we have some problems here that I think it should also be important as the AI models where you guys are trying to optimize MPI or reduce for them, because this is a bottleneck. It's the same thing here. We need some kind of optimization to this MPI step. Also, when we talk about Grace Hopper chip, we were able to reach to 2.56 billion point using 512 GPU. This is also because of the memory. Here we have 40 gigabyte GPU. Here we are talking about 96 GPU. And also you can see the same problem of scalability. If we scale more, we didn't try more than this, I think we will have a very serious bottleneck related to the MPI process. Let's talk about the power consumption. I'm almost done. About power consumption, of course, when we talk about GPU, all the people now caring about the power consumption, how much you are consuming, and surprisingly, you will see that this is our power consumption per GPU for the A100 and for the Grace Hopper. But one thing is very important, that we did the same power consumption process using our old method of MLE without approximation, and we on one GPU we found that using VK approximation can save more than 99.5% of the power consumption doing the same thing exactly as the normal MLE. So if we have the same data set using the traditional method and using the approximation method, we can save a lot of power just by using VK approximation. So the take-home message of my presentation, that climate weather models actually depend mainly on communication, and they have an I/O bottleneck on traditional HPC. It seems that we need to move from this old way and maybe take something like AI if they can confirm their capabilities to do modeling and forecasting, or to use spatial statistics for modeling climate weather data. Also, those kind of workload may be also better to use some kind of approximation or energy efficient algorithm to help using the hardware in a very efficient way. Gaussian process modeling can be used in different applications, not just for climate weather modeling, and approximating it using VK approximation with different variant of it, it's very important. Reducing the power consumption across multiple GPUs is very obvious, shown by our figure compared to the old method. And again, the application is not just related to climate weather, but also can be used in different domains. These are 3 references, one ISC paper in 2024. We have another paper on a very prestigious statistical journal called Technometrics, and we have a recent archive paper related to the distributed result that I showed in my presentation. Thank you so much.
So let's give thanks to Sameh. So I think I saw Pankaj, you have raised a hand. Please unmute him. You can ask the question.
Yeah, thanks, TK. Thanks for a good talk, Sameh. I have a question about versus Legendre and Fourier transforms, which can capture global phenomena like circulations. Such nearest neighbor methods are more local in their correlative structure. So do you have some Fourier-like things in your nearest neighbor selection that help you model circulations and fluxes at global scale?
Yeah,
like
I
jet
agree.
stream or...
Okay,
Yeah.
I agree with you. I think nearest neighbor is something simple that we picked just to make everything works. And maybe it's a bottleneck because of that. Yeah, we are in the process of actually optimizing this and have some Fourier-based method or other methods just to reduce the communication locally between different processing units. But until now, no, we just have a normal nearest neighbor algorithm.
Okay, and I think second quick question was about indexes. So, you know, similar distance consideration for organizing a lot of data points are used in RAG, where you can have even 1400 dimensions, not just 15. But they use arbitrary partitioning of dimensions for compression. So I wonder if you could borrow from RAG structure like DiskNN or Meta's FACE to organize your data for nearest neighbor search. It's just a suggestion.
Yeah, I think it's a good point. I'm not aware of this. Maybe we can take a look also to see if this will help on the partitioning part, right? You mean on step 1?
Yes.
Yes. Okay. Maybe we can
I think overall structure